Another important person of that scientific school is Alan Mishinka. Alan Mishinka, known as a developer of ABC tool, a fast and scalable solution used, for example, in OpenLane. The second well-known scientific school is L'École Polytechnique Fédérale de Lausanne. It's headed by Giovanni De Michele. This school is famous for their theoretical results in, for example, majority logic synthesis with applications to some advanced technologies like QC8, quantum cellular automata, and so on. Besides some theoretical results, his team developed tools and libraries such as Mock Turtle, Kitty, Percy, Lorena, etc. I think all of you are familiar with OpenLane design flow. This is automated RTL to GDS2 design flow based on open source tools like OpenRoad, Yosys, K-Layout, and many others. Speaking about logic synthesis in OpenLane is based on Yosys tool. Yosys is a well-known tool. It has been developed since 2012. It supports Verilog 2005, contains many synthesis and optimization processes. There are front ends for system Verilog. One of them is based on Slung. It's open source. The tool is extensible. One can implement optimization process or front ends or back ends. Okay, so we have Yosys, we have ABC, we have Mock Turtle. Why do we need another logic synthesis tool? The main explanation here is education. We started this project as a part of our activity, our education activity. Institute for System Programming started so-called project activity in Moscow Institute of Mathematics and Electronics a couple of years ago. And Utopia was a playground where students can try their algorithm, their synthesis algorithm, their optimization algorithm, compare them, evaluate them. And we think it's really important for students to not only to know how circuits are optimized theoretically, but to know how EDA tools are organized under the hood. So that's the main explanation. However, there might be one more question. Why not to use ABC or other open source tool for that? I think the main answer here is that ABC is very complicated. It's written in PVC, there are lots of optimization tricks. Architecture is not very clear. So probably it's a good tool for advanced level, but not for beginners. So that's the main question, main answer, I think. The second reason why we started that project is research. Utopia for us is a playground. It's a playground not only for students, but for researchers as well, for mastering new methods or for updating, for changing, modifying some existing ones. And the third answer is industry. Utopia is used in a couple of industrial projects conducted at our institute. Okay, let us consider top-level entities, top-level concepts Utopia works with. There are two such entities, net and design. Net and design represent the same things in different ways. Net is how input data looks like. Design is mostly intermediate representation suitable for transformation and analysis. net is a hierarchical net list. It consists of logic gates, of flip-flops and latches, of soft blocks, which are microcells with known implementation or at least known functionality, and hard blocks, macrocells with unknown functionality. Design is a net that is, first of all, decomposed, flattened. All soft blocks are inlined. And secondly, decomposed into combinational subnets, hard blocks, and flip-flops. The main entity Utopia deals with is combinational subnet. It's represented as topologically sorted sequence of cells. Technology independent and technology dependent subnets are represented in the same way. The difference is in cell types. Beside cell types, cells consist such information as symbol, which distinguish a function cell implements, properties which are additional flags used to subdivide cells into combinational, sequential, soft, hard, commutative or non-commutative, and so on, and links. Subnet consists of links directed from target to sources. So each cell contains ingoing links. So we can reach sources of that cell. Outgoing links are not stored, but they can be constructed on demand. Instead of keeping outgoing links, each cell contains a ref count, reference count, which indicate how many times this cell is used by another cells. Another important notion is subnet view. Subnet view is subnet fragment. It's represented by point to the parent subnet and by input-output boundary. Okay, and here is a bit simplified view on subnet transformation API. We have functions to replace given cell by another one. We have functions to evaluate cost of replacement and to perform replacement itself, and function for merging cells into one, with redirecting links directed to cells to the cells being removed to the remaining one. Logic optimization is known to be a very computationally hard problem. In most formulation, logic optimization is sigma to p complete, which is the next complexity level after NP. So it means that there is no way to produce optimal solution. So that's why logic optimization is usually done iteratively by a replacement of small fragments of subnets. Typical procedure looks as follows. For each cell in topological order from inputs to outputs, different fragments are constructed. For each fragment, we try to resynthesize that fragment to construct better fragment. I mean fragment such that replacement will lead to better subnet in terms of number of gates or depths. There are two main approaches to resynthesize subnet fragments. One of them is to use pre-generated database. And the second approach is to synthesize circuit on the fly. Here is some implementation details. So we have a target subnet represented as inverted graph Inverted graph is a method for subnet representation where each cell implements some logic function like AND or exclusive or, but inverters are located on the links, not in the nodes. Fragment enumerator enumerates different types of fragments. Key feasible cuts, for example, multi-level cones. There are two additional components. One of them is called functional IR constructor. It captures functionality of a subnet fragment in terms of truth tables, binary decision diagrams, or in some other way. Context analyzer analyzes a bigger fragment, so-called context, and tries to capture so-called don't care conditions. Combinations where output value is not important. So it adds some flexibility to synthesis, providing, making it possible to synthesize small circuits. Okay, this slide shows available transformation. So we have constant propagation, functional reduction, which is finding equivalent cells in subnet and merging them. Rewriting, iterative replacement based on pre-generated database, refactoring, iterative replacement based on on-the-fly resynthesis, and resubstitution, which is implementing cell functions by finding dependency function that describes cell function through the neighboring cells. Technology mapping. The goal of technology mapping is to find optimal or at least appropriate cover of technology independent, at least by technological cells. The main mathematical engine here is dynamic programming. When technological library is loaded, it is supplemented with so-called supercells, which are combinations of or superpositions of ordinary cells. And for each cell or supercell, index or hash is calculated. As a result, we have indexed library. To find cover of target subnet, again we have so-called fragment enumerator that divide subnet into pieces. And for each piece, the same kind of index is calculated to and fragment match technological cell if the index calculated for the fragment is equal to the index calculated for the cell. If there are multiple matches, special components, so-called match estimator, choose the better solution. For the moment, we support Boolean matching, which means that index is, roughly speaking, is truth table. So we have technological cell, we calculate truth table for that cell. We have subnet fragment, we calculate truth table for that fragment. To be more precise, it's not actually a truth table, it's so-called canonized truth table, canonical representative of p-equivalent functions. It has functions that can be constructed one from each other by variable permutation. Another support techniques are fragment prioritization and some heuristics to calculate area and flow, so-called area flow heuristics and power flow heuristics. Okay, and to make sure that all transformation preserve functionality, logic equivalence checking is used. Two circuits, obviously two circuits are logically equivalent if they produce the same result and the same inputs. In other words, their composition, so-called, might always produce zero or unsatisfiable. There are some techniques to check might unsatisfiability. The basic methods, trivial methods, are based on binary decision diagrams and on SAT solvers. I mean, straightforward using of SAT solvers. Encoding might into conjunctive normal form and then checking their unsatisfiability. There are more sophisticated methods implemented in Utopia. One of them is based on iterative functional reduction. The idea is to find equivalent points, merge them, and to launch SAT solvers with increasing time budget. Also, we have implemented iterative decomposition where the tool keeps track of merging points again and cut the circuit in a way that upper part, a part that closer to inputs, is thrown away, while a lower part, which is closer to output, is used for checking. So that's provide more scalable solution, but at the same time, there is one important drawback. There might be false positives. Here is a typical use case. Utopia is organized from the user point of view as a typical shell. Here are some typical comments. First of all, we redesign. Here, for example, we use read.ftml. As for Verilog and system Verilog, that part of Utopia is unfortunately closed. The second comment, save checkpoint to be checked in the future. Then local AIG, pre-map design in AIG and inverted graph. Comment after that, perform logic optimization, sequence of optimization passes, balance, rewrite, balance, refactor, balance, resubstitute, and balance again. The next two comments, save checkpoint and lag compares two checkpoints against each other. Then it comes read liberty. We read technological library and then perform technology mapping. The objective here is area. And finally, we have also checkpoint, checking equivalence once again, and printing technologically mapped netlist into Verilog file. A few words about our ongoing and future works. We are planning to integrate Utopia with Zwirt, which is a circuit IR compiler and tools, MLIR-based project for digital hardware design. We are thinking on scalable algorithms for logic equivalence checking, because the algorithm mentioned previously are not very scalable. We are working on high-level synthesis. Actually, it's not a classical high-level synthesis for C and C++. It's more like high-level design for particular class of designs, namely for streaming data computers, streaming data flow computers. Some works are unfortunately closed. They are done on commercial basis. Amongst those jobs are FSM-based optimization techniques and timing. We are working on using AI and ML in logic synthesis. And big topic is formal verification. Here are my contact information and Utopia-related links. Utopia EDA itself, Utopia HLS, a separate project. Results as a Liberty parser used in Utopia EDA. So thank you very much.
Thank you very much. Talk and maybe one or two questions.
What do you need to simplify the synthesis for beginners?
Please repeat the question.
What do you need for simplicity the synthesis process for beginners? You said that software is simpler than another tools on the market.
Okay, thank you. My talk was about not to simplify synthesis itself, but to simplify education in the field of logic synthesis.
From the script I saw, that is like a general synthesis tool. Not a lot of difference, I can say. It is simpler by definition of level of optimization, but not clearly that is really simpler to understand in comparison with the different software.
Yes, exactly. So synthesis itself, from the user point of view, it looks the same. It's not simpler. The problem I'm discussing is how to teach students to develop EDA tools, how to develop logic synthesizers, to how logic synthesis is organized inside, under the hood.
Did someone try to apply this software in industry?
We are applying in 2 projects.
Tell more.
No.
Thanks.
Well, I can actually add a little bit to this thing. Like, I'm not familiar with his tool, but actually there is some value even in a simplified synthesis. So, for instance, if you get like modern tools, Synopsys RTL Architect, this is like a physical compiler for like RTL engineers. So like this is a tool which is like similar to a Synopsys IC compiler, but it doesn't go all the way to GDS2 file. It goes only to reports. And basically, it doesn't even produce accurate reports. So actually, if you synthesize it, it can tell you that this has like the maximum frequency, like of like let's say like gigahertz, and like it like occupies the following area. Like actual synthesis result might be different. However, with this tool, you can have estimation for the comparison. So you can get your Verilog, create a like reference point, and then do some microarchitectural changes and synthesize again and get another reference point, and you can see how much gain percentage-wise you can get without doing the whole synthesis. And actually, you can do this much faster than using regular synthesis tool. So with a regular Synopsys IC compiler, it can run for you like 20 hours. But with this thing, it will run in like 1 hour, and you will get your report. Then like it also used AI to do some variations, so you can actually study different variants of your design and make some like approximation. So like even if this tool is not fully optimized, you can still get value because it can be used for like comparison of quality of your design and for doing some like experiments. You know, so so this is both for students to learn EDA algorithm and to do a rough estimation for his design.
Okay, I would suggest to continue discussion during the coffee break because we already running late, maybe 15 minutes. So let's hear the next talk. Then we will have a coffee break and we can discuss all the things with each other. Okay? So thank you very much. And before the coffee break, the last talk will be delivered by